This week we're going to look at simplex range searching problem. This problem is a data structure problem defined as follows. We have a set of endpoints in the plane and we want to store them in a data structure such that given a query rectangle we can either list the points inside the rectangle or the number of points inside the rectangle, etc. The data structure that we're going to introduce for this problem actually can do all of these types of queries and actually much more. So you can even find the point with the maximum weight if their weight assigned to the points and so on. So for example, if your query is like this, and the answer could be 3 or the list of those 3 points, etc. I will go over the known results. So these are the best known results for this problem. In general, you have two categories of problem. You have the low space solutions. These solutions take linear space and the query time is roughly square root n. So if you want to count the number of points inside the triangle, you spend square root time. If you want to report square root n plus k, where k is the size of the output. Obviously, the plus k part is optimal because to list the k points, you need to spend k time anyways. But the square root 10 is high. Or if you want the query time to be polylogarithmic or in particular log, if you want very fast queries, but you have to spend n squared space. There are lower bounds in some models of computation that show essentially both of these extremes are optimal or close to optimal. So you can't do it better than this. You can combine them. So for example, you could have a trade-off in between. So you could increase the query time, let's say from log n to some t, and then you could reduce the space by a factor t squared as a sort of consequence. So basically this means that if you want to go the query time to be square root n, the space goes down by square root n squared, which is n, so therefore you get this linear space. So you can actually achieve a balance between the two if you want to. But you can't do better than these. I remarked that to get these results, we need to use essentially two major tools in computational geometry, the partition tree as well as the cutting lemma. Proving both of these, or proving either of them actually, is beyond the scope of this course, and it requires a PhD level course. In particular, cutting lemma ties very deeply to VC dimensions and epsilon nets and random sampling techniques. And similarly, partition tree, there are many different ways to build partition tree nowadays. There is also a relatively new algebraic revolution that you can use higher dimensional theorems such as ham sandwich cut to get these partition trees. So they are definitely beyond, proving them is definitely beyond the scope of this course. But using them to get data structure that are close to these bounds, it is within the scope of this course, and that's what we're going to do. So in the next videos, I'm going to talk each one of these directions, and we're going to see how we can reproduce or almost reproduce some of these results.